In this video, we're going to look at, as the title suggests, two methods. One's called halving the interval and the other one's called Newton's method. We're looking at these two methods and how we can use those to find approximate roots of an equation. Now, hopefully you understand that the roots of an equation, they're best understood graphically, and it means where if we were drawing the graph of a function or an equation, where would the graph actually cut the x-axis? That's graphically. And what does that equate to? That means where is the function equal to 0? Now, one of the interesting things about having these in this chapter is that it's totally different. It's got nothing to do necessarily with trig. It could be a trig function, but it may not. And it's nothing to do with integration, as the previous two exercises were. And in fact, one of these methods has nothing to do with calculus at all. So the fact that it appears here in this chapter called Further Calculus, it is really doesn't really fit. But these two methods are extension 1 concepts, and don't assume that means they're difficult. They're definitely not. This first method, called halving the interval, actually could have been introduced in year 9, no later than year 9, when you're getting right into graphing a function and looking at where it cuts the x-axis, because that is all it's about. It's all about where does the graph cut the x-axis. And the reason that you might be wondering, why do we need this approximating the roots? Well, there are some functions that it's impossible to solve equal to 0. However, the graph of the function will cut the x-axis somewhere. So, or if it's very difficult to solve. So if you want to get some close value, these are the methods for getting the values for where the function would actually cut the x-axis, or the function would actually be equal to 0. So they have nothing to do with one another, except that they both give an approximation for where the graph would cut the x-axis. That's the only thing they've got in common. So they're treated very separately, although they're both here in this one exercise. And keep in mind, this is something that will only appear in an extension exam. You would be asked to either establish that the approximate root of a function is, and it might give you some values, or the instruction might be use half the interval method, or use Newton's method to find an approximate root. So you have to be familiar with the two different methods and don't get them mixed up. And I think the first one, which is halving the interval, which we'll look at first, it's really self-explanatory. We're going to keep halving an interval. So, having established that this whole concept is about where on this x-axis would a function cut it. If a function the graph of a function is only going to cut it if at one stage we're either above the axis and at one stage the y value, followed then by a y value that is below the axis. So going from x1 to x2, we've gone from above to below, then yes, clearly there is a root here in between x1 and x2. I guess the other option is we were below the x-axis and then we went above the x-axis. So over here at another x value, when we move from there we're below and then we go above, we have another root here. So this method is based on that simple concept that the y values or the function values go from either being negative values, as we're down here in the negative y's, up to positive values. And in between, if you can establish there's a little interval between two x values, and they're namely called a and b, between a and b, if you go from a negative y value to a positive y value, a root must have occurred. Or if you've gone from a positive y value down to a negative, also a root must have occurred. You could probably see that then between x2 and x3, if we then got another negative value, we don't know whether this is doing that or if it's going like that, but we know that there's between two negative y values or function values, no root is occurring. Unless, of course, it zipped up and came back, and in that case, we would have to be given some clearer indication of this, how big the interval will be. So, and that will always be the case. You won't get this sort of thing happening because the questions are going to be set up such that you can see you've got a negative y value and then a positive y value, or a positive y value and then a negative y value within the interval of x values that you've been given. So you'll be halving this interval. Why would we halve it? Well, as you can see, if we were given the original interval as going from a to b, it's easy to establish that a root can occur because the function at a is a negative, isn't it? The y value, when I sub a in, is a negative value. We're down below the axis. And the function value at b is a positive value, so the y's have gone from a negative to a positive. Within this interval, that means the graph must have cut the axis. Well, what we can then do is test the middle. Test the middle value. And the middle value would be halfway between a and b. Add the two together and divide by 2. Obviously, if you work out that the function value of halfway is also a negative, if that is also negative, we can see in this example it is a negative. So the function value at a was negative, halfway it's still negative, but then at b it's positive. We know that the root occurs now within this smaller interval from halfway up to b. Then again, we could test the halfway point again. And if the halfway point, if that point now gives me y is 0, then I've found the root. However, if at halfway we were still above, let's just say halfway between these two now is here, and whoops, the function, no, we want the other way, sorry. Let's say we've established now this halfway point, the function value was a positive number. So we don't want to go this interval because it was positive here and it's positive there. There was no cutting the axis. But at the previous interval, from there it was a negative, the y value was a negative, then the y value becomes a positive. So we can see that within this smaller interval now, a root must occur. And we just continue to find the middle of each interval until we're getting our interval closer and closer to the actual root. So that is all that this method requires. The thing you will be doing is substituting values into a function. So, like I said, that was a year 9 or even a year 8 concept, where you sub values. You strategically have to pick your values, and your values are based on these points in the middle of an interval. and then we strategically keep readjusting our interval until we're getting closer and closer to where the root is actually occurring. And as it says here, this whole method is based on trial and error. It's just trial and error. So it does depend on how careful you are with substituting your values and deciding or identifying whether you've got a positive result or a negative result. So let's have a look. This method involves finding two x values, namely a and b, and they've got to be fairly close, your a and your b, and you're often given them anyway, so that's fine, where one results in a positive y value. So here at b, if we subbed in b into the function, we're clearly getting a positive y value. And if we sub in x into our function, we're clearly getting a negative y value. So if our function over this interval from a to b went from a negative y, that means the graph was below the x-axis, to a positive, was above the x-axis, it clearly crossed the axis. That's called the root. What we then consider is, and it actually doesn't look like that right there in the middle of the interval a to b, that we do get a root, but if right at the middle of your interval you sub that value, so if this was 2 and that was, let's make it 4, then right in the middle is 3. If we found the function at 3 was actually equal to 0, we'd say a root occurs at x is equal to 3. More often than not, you'll find it doesn't, and you'll get more likely this situation. So at the middle point, so let's just make this easy, 1 and 3, so now we're at x is equal to 2. At x is equal to 2, we're just getting a slight positive. What do we know? We were positive at 2, we were negative at 1. The root now occurs between 1 and 2. We can narrow it down. So we would take halfway between 1 and 2. Halfway between 1 and 2 is the interval from 1.5. And at 1.5 we can see that our function is negative. So now I'm going to go this interval in here, somewhere between 1.5 and 2, because at 1.5 the y value is negative, at 2 it is positive, and so on. It's all about trial and error. It's all about finding y values, which is such a simple concept. Sub into the function a value for x and you'll get a y value. And so you could see here that if this was the situation, then we would reevaluate where the root was. We can shorten our interval from a plus b on 2 to b and find the middle of that. So we would be estimating it's around that value, halfway between. But of course, if we found that the graph was doing this, and this is our a plus b on 2, halfway between the two, then we would say that the root is somewhere between these two, or halfway between these two. So we add the two together and divide by 2. And there's lots more simplifying that can go on, but that's just simplifying algebraic fraction work. I'll stop the video there and I'll go through this example in another video.